Hi. At the end of the last video, I came across a number of issues that I felt were significant enough that they were going to take a little bit to solve. I didn't want to tack them onto the end of the last video because I figured the video would end up pushing close to an hour, and I don't think that's effective use of your time. And I know it's difficult for me to pull that together and release it. So I ended up kicking a number of things down the road, and the point of today's video is to see if we can get through all of those. So one of those issues ended up being that the byted address 0 was being overwritten with the contents of 7FFF. And that's a bit of a disconcerting thing. I can work around it, but I'd rather have it right before I send out for PCBs. And I do want to send out for PCBs relatively quickly on this. I also uncovered that there were some crossed wires on the SRAM for the I/O pins, and I need to get to the bottom of that to make sure that those are actually working properly. While they could likely work as they are now, I want to just double check and make sure that they're working exactly the way that they should be. I never got a chance to test out the mid-speed clock. Now that is about a 1.8 megahertz clock, and the high-speed clock, which is about a 10 megahertz clock. Both of those are crystal oscillators. And then I really did hope that I could get into the PCB design for both the control ROM module and the control ROM control circuitry, as well as the backplane to support those. And I never got to those. And honestly, with what I've got going on, I may or may not be able to get to them in this video. I want to confirm my behavior in the emulator to make sure it's matching what I'm seeing on the hardware. And we've got a lot to do. So let's get right into all that.
Hi, I'm Adam. I'm still building a 16-bit computer from scratch. I'm no expert here. I make lots of mistakes. So many mistakes I've actually had to reboot my computer build. I hope you will find my journey interesting, and I hope you will join me as I learn along the way. The first order of business today is going to be to check the emulator. I want to make sure that I'm getting the same behavior in the emulator that I am in the hardware build. And that behavior that I'm looking for is that both the first byte and the last byte get updated just like the hardware was showing me. So what I did is I made a change so that the most significant byte on each of the EEPROMs gets programmed with FF. Then I also made another change to the emulator, and I cleaned up the comparisons here so that I can clearly identify exactly where the problem is and output what I found and what the contents actually were. Let's run it and see what we get. Yeah, that's a problem. So it looks like the very last byte is not getting updated. It was supposed to be updated to FF, and it really was 0 or 00 in hex. That tells me I've got still a difference between the emulator and the hardware. And I guess the question now becomes, well, several questions. One, is it significant enough to do something about? Well, the SRAM is not faithfully representing the EEPROM. So, yeah, I think it's a problem. The second question that brings up then is, can I live with it? And I don't think I can. I think I need to get to the bottom of this and figure out a way to make sure that everything gets copied. How to do that? Boy, the devil's in the details. I've got a first iteration, last iteration problem, meaning that there's something that goes wrong with the first time you run through a loop or the last time you run through the loop. Either you're not priming it right or you're not basically exiting the loop properly. At least that's the way I describe it when I'm dealing with software. The problem is this is not the first cycle of the loop, it's the last cycle of the loop, and I've got some close to 300,000 clock ticks that I've got to get through in order to experience what the problem is. That's a little excessive for single stepping or running and then trying to stop it at the right point in time. Well, I've got a more powerful circuit here that I'm going to turn around and use to try to control that. And the first thing I want to do is actually have the ESP32 operate this reset button for me. And I think I can do that relatively simply, but I also want to make sure I don't blow this up. And so these are the same BJT transistors that I've been looking at and using down here as part of the test rig. And so what I should be able to do then is take and hook up the base from the transistor up to the ESP32 somewhere. I'll need to get a limiting resistor in there. But that should then allow the ESP32 to assert a signal onto this wire, which then would cause this transistor to operate. By opening or allowing current to flow from collector to emitter, that should effectively do the same thing as me pushing this button here. That's the theory. Let me get the datasheet out and double check this, and then I'm going to do some testing with just simply 3.3 volts and ground right out of the chute here, just to see how that's going to behave for me. Let me start there. So what I did is I added a 1000 ohm resistor down here. This is connected to the 3.3 volt pin, so that I should be able to tie this to 3.3 volts and see this open and have this circuit go into reset. So let's give that a shot. And so now if I'm in ground, let me turn that into run mode. Keep an eye here, and that's properly reset. Properly reset. So that tells me I should be able to actually get the ESP32 now to operate that reset. I'm just basically going to move one line down here in the chain and reposition my resistor, if I can do it without dropping it. Now I need to update the sketch to hold this in reset until I am prepared to let it rip. That's step number one. Okay, the next step along the way here is I want to remove the clock circuit from this test rig and drive the clock specifically from the ESP32. Now, to do that, it's going to end up looking very much like these inverters here, which means that I'm going to have to actually invert once in software, once here in hardware, in order to drive this clock circuit. So let me start by removing the clock module from here, and then we'll wire up another transistor here with the current limiting resistor on the base. Okay, now that's not going to work until I actually program the ESP32. So let me do that. We'll come back with a test. All right, simple change here. The ESP32 should now be providing the clock to the circuit here. But at least the clock is ticking. That's good. So I'm going to let this run all the way through just to make sure that nothing breaks. Okay, the failure at address 1 is new. All right, let me set up some single steps here for the first few bytes so I can figure out where this is coming from. Okay, I ended up doing some probing and inverting that clock in software, and that put me back to the original problem. All right, the next order of business here is going to be to have the ESP32 actually stop the clock when we get close to the upper limit here of the address range. Now I'm counting clock ticks, and recall that I've got 32,768 bytes plus 3 additional bytes for commands that are being shifted off this IC here. And then I want to stop it before the last byte is being shifted so that I can actually observe what's going on with the final shift and how the entire circuit shuts down. It takes about 10 minutes for the ESP32 to actually run through everything, so it's not a quick test cycle. So I will likely, once I get it working and have it stop, I'll probably set up several things and try to monitor this as closely as I can. I'm not exactly sure how that's going to work, but let's start with a software piece of this, and then I'll come back and actually see if I can capture it stopping. Okay, well this definitely falls into the, well that ain't right category. So my yellow trace is hooked up to the right enable pin on the SRAM. The blue trace here is hooked up to bit 0 of the address that's going off to the SRAM. And I was able to get it to stop, and I was able to step my way through this, and I'll demonstrate this through one of these cycles. But when it performs its reset, what's happening is you can see that the write enable is coming low. While it is low, the address is changing to 0, and then it's going back high again. Well, that ain't right. I don't have any answers as to why yet. So I've actually run this probably about a dozen times, taking about 10 minutes a piece to get through the entire cycle. I think I need to compare, not to bit 0, but I think I need to go over here to the multiplexers that are multiplexing the address coming in off the bus versus what's being driven by these counter ICs, and see if I can't get that working. Or not working, but see if I can't measure what that is going to be. So I'll just reset here. The write enable is driving this, and then once we get to the end, we'll walk our way through that. Okay, so we hit the breakpoint, and we'll put air quotes around that. Once again, my yellow trace is the write enable, and that's stopping on when it goes high. And then I've got the selection for the multiplexers as the blue trace. If you pay close attention here, this is going to latch, and it's going to very slightly change the display. And then there was the increment. So now I need to get to the last, and you can see that my selection is falling as to what is being presented through the multiplexers before that latch actually takes place. Okay, I've got what I believe to be a test that positively proves where the problem is and what the electrical solution is. If you can look down here, this signal here has been removed from the selector of the multiplexers and is set aside. I have that signal right now directly pulled high. What I'm going to do is I'm going to go through the copy. The ESP32 is going to stop at that point. I'm going to switch that signal over from high to low, indicating a change, and then we should be able to go through and validate all of the data. Well, what's different? What I get is I get an extra clock cycle in there where I can actually manage the transition from high to low at basically a half a clock cycle later. And that's all I need in order to get this to work. So let me reset. I will off screen hit enter to get this started. So then once this is done copying, then we'll come back to the ESP32. Okay, the copy is now complete. Let me bring it up side by side. I have a prompt here. I'm waiting for the low clock. If I hit enter, that clock is now low. If I change this select to be low, it is now getting its address from the shift, which is being driven by the ESP32. And then therefore, when I hit enter again, it will begin its check. And look at that. That's actually a successful test. So now I just need to figure out how to manage this signal and delay it by half of a clock. And I actually have a plan. Recall that this D-type latch, I'm only using one of the latches on that IC. I have a free one up here. And I'm already taking and inverting the raw copy clock so I can extend that up there as well. My expectation is that's going to delay the QC signal, if I feed it in, by half of a clock cycle. So then I can drag that over here to this signal here to control what the multiplexers are putting out. And then I just need to change the input for the open drain NAND gate to be off of this as well, so that it stays, the circuit stays in reset for that extra half of a clock cycle. I have a plan. Okay, that's great, Adam. What exactly is it you're talking about changing here? Well, I've got this QC signal up here, which goes into the reset hold, basically saying that the copy is completed. And then I've got these 4 QC signals down here, which flip the multiplexers from the counter ICs to the instruction bus coming in. And I need to delay that by half of a clock tick. So I've got this unused gate down here, which is a D-type latch. It's the same thing I've got up here. And I'm going to redraw this up here just to make it a little bit easier to see. So my outputs here are Q and not Q. I've got set up here and reset down here. And then I've got my clock and my data pin. These two are outputs, obviously, control signals, and my inputs. Now, just like up here, I've got a reset coming in, and this is the core reset signal coming in off board. So that's going to be there, and then the set is going to be tied to VCC, so that when the reset starts, it'll pull this signal high, and this then will be my new done signal. This signal will end up going to these locations now. How do I manage that? Well, just like up here, I've got a raw copy clock, which is inverted. I'm going to use the same thing here. And so that'll be my clock. That way, this is in phase with this. And finally, what am I going to use for my data? Well, that's going to be very simply QC. Let's change the emulator first. So I came across a couple of bugs that I needed to solve, but there was one thing in particular that I want to call attention to. And this is on the control ROM circuit itself. And this enable signal here is for the line driver, which drives the outputs off the shift register out onto the bus that the SRAM uses for latching. Now, this signal was the not QC signal. So why did I have a problem with that? Well, the problem was the way the emulator was working is it would not complete its sanity check properly. And more to the point, while the signal write enable was low, all of these values would turn off, which meant that it would go through and individually update this while this write enable signal was low. And so I needed to delay the disable of this line driver until after that had been completed. So what did I replace that signal with? Well, this same D-type latch has an inverted signal, which I turned around and passed off to the control ROM itself, updating this signal here. Now I've got QR, not QR, QC, not QC, QS. I've got all of them here, and I'm probably going to whittle this down as I get into the PCB design. I'm certain I don't need all of these, and certainly over here, these need to be named better anyway. So I'll doctor those up when I get ready to get into the PCB. At the same time, I'm likely to remove the signals here for what is actually active so that I no longer have those LEDs, and I'll be able to save an IC there as well. All right, so let's go over and take a look at the emulator. And as you can see, I've still got a little bit of debugging code in the background, but the important bit is here, where the result of the sanity check is that the data is still sane. That is a good milestone. All right, let me get the breadboard build cleaned up, and we'll give this a shot there as well. Okay, the first order of business is to set up this upper D-type latch. Now, this down here I don't need anymore, so I am going to borrow from here so that I can make these changes up here. The output Q is on pin 9. Pin 9 needs to go to that location there. And then I'm going to pull the input here. And this signal will then come down here. So that takes care of all my QC changes. Now there's one more change I need to make, and that's this not QC. This one goes up here to be taken off board, and I need to drop that there. I believe that's all the hardware changes I need to make. Let me launch the Arduino interface. Power that on. Power that on. Everything's powered up properly. And we'll reset. I won't make you sit through all of this again. Let's jump to the final stages here. That is a good test. The next thing I want to do is I want to replace the clock coming off this ESP32 with this 1.8-ish megahertz crystal oscillator. Now the clock signal will be here, and that allows me to drop that in there. This signal then becomes obsolete, so I'll just tuck that right up here for now. But I've got to change the code here on the ESP32 to not provide that clock. So let me get that changed and we'll come back and test that. Okay, relatively simple change. Let me get everything powered on. I will program the ESP32. Okay, here we go. One of the things I like about this is it doesn't take long to actually go through the program cycle. Unfortunately, it does take a lot longer to verify. So I'll come back at the end and I'll report the results. That's also a good test. I also have a 10 megahertz crystal here that I want to give this a try with. Now, in all honesty, I am not expecting this to work, but I just want to do it just so that I know one way or the other if this is actually going to be feasible or not. So I'll pull out that crystal and I'll drop this one in place. And that should be oscillating at 10 megahertz. So I reset again, hitting enter to go. And yeah, that failed almost immediately. You can see that the address location 1 did not get updated properly. So the 10 megahertz crystal is out. I wasn't expecting anything different, really. The 1.8 megahertz crystal stays because that allows me to do a quick reset. And now I need to pull the ESP32 out of the circuit and start a tidy up here. Okay, I have adjusted my camera angle because the stuff down here is all going to be removed, and so this is the piece of the build that I want to focus on. I did find an issue, and that is that this signal here, which is the output enable for the latch, wasn't ever hooked up. Instead, I had tied that low, which was incorrect to do. And so what do I need to do? I need to remove this. And for now, I'm just going to take third from the top. It should be this one. And I'll just tie that here. I've made a change. I need to test. That was a good change. Okay, the next thing is to replace this with something a little bit more permanent. Okay, the next order of business is going to be these 3 signals here. And I'll bend them down so that you can see them just a hair better. Now the challenge here is that bit 0 is going to bit 2 and bit 2 is going to bit 0. So these outer 2 need to be reconfigured. The inner one is fine because it's going from bit 1 to bit 1. Okay, and I test again. That's a good test too. Okay, the next issue is actually pretty interesting. The last value that should be displayed is AA, but instead I have 55 being displayed. Well, the root of this problem is actually twofold. What is on the LEDs is actually accurate to what was loaded onto the SRAM. But down here on the ESP32, I managed to get these signals defined incorrectly. I have this as bit 7 and that is bit 0. It should be the other way around. But then that creates an input problem. And I believe I have all of these signals wired incorrectly as well, coming off the shift register into the line driver. And if that's the case, then I'm going to have to check the pin outs of the 164. Let me make the software change here, and then I'll bring up the pin diagram, and we'll take a look at this together. Okay, and with that quick change, you can see that I am now reading the incorrect value in address 1, which I expected. So let's get the 164 up and take a look at that. Yeah, with the 74HC164, I took the most significant bit off of here and connected it to the least significant bit on the line driver. So every one of these connections is incorrect. So I need to revisit these. Let's power off before I do this. Okay, and yet another test. Nice. And you'll notice that the end result, the final answer is AA. Even better. Okay, the next step here is to clean up all of these temporary wires. While I'm here, I'm going to clean up some of these shorter wires here on this hookup, just to make sure that they are handled properly. Okay, time for another test. And that's a good test. The next thing I want to tackle is cleaning up some of the control ROM module concerns in the schematic. There's a few things that I think need to be renamed, and one minor change I think needs to be made. All right, for the renames, I want to change this to be the CPU clock. And the reason I want to call it CPU clock is I want there to be no opportunity for ambiguity between that and the copy clock or any other clock that might be on the system. This is going to be the main CPU clock. The next one on the list is this one, which is going to be the latch output enable. And I believe that's the way to do that. And again, that becomes the output enable on the latch here. All right, that's going to be the shifter output enable, which is really basically on the line driver. And finally will be the shifter reset. In case you haven't realized that I'm using all uppercase to indicate signals that go off the particular module. So each of these are all uppercase now. And again, an ERC, no issues. And the last thing I want to do is I actually want to add a second capacitor for the power, because I have actually 2 pins which are voltage input. I want to make sure I've got a capacitor for each one. That sets me up to be able to start working on a PCB design here. Let's get that going. Okay, first thing is to assign some footprints. Okay, let's get into the PCB design. That has the wrong footprint. Okay, the only one that absolutely positively has to be on top is going to be the socket. Here I'm just playing around with a couple of thoughts on how to position all the components. There's a lot of room here left to right, so if I make it a little bit taller, can I condense it a little bit? Now to try to squeeze in the decoupling capacitors. Not too bad as a first look. Okay, I'm not certain I like the footprint of this SRAM. I'm likely to use an SOIC rather than a DIP, so I need to go see if I can figure out exactly how I can get this SRAM. Okay, so I can get it in a 28-pin SOP package, which is in line with what I've been using. Okay, so this ends up being slightly different widths than most SOIC packages, and I decided to look on DigiKey to see if I could download for KiCad some footprints that I could use. Guess what I found? Okay, so that change allows me to start looking at what it's going to take to consolidate and reduce the size of the PCB. And here I start the long process of looking at pin by pin to see where each signal is routed. I'm looking for opportunities to reorganize the layout so that I don't have traces running all over everything. I'm hoping to make this a simple route. For this part of the process, I spend a lot of time looking at the screen and thinking about what the routing is going to look like. I've not tried to place a single trace yet. Okay, I think I'm probably 40, maybe 45 minutes into this. I'm pretty happy with the way that this PCB layout turns out. Now, I've just done component placement. I have not done anything related to cleaning up silkscreen or running any of the traces, dealing with any of the rat's nest. I think I'm in pretty good shape here. I actually spent quite a bit of effort looking at individual traces and trying to figure out the best way to make sure that everything actually lined up right, so I didn't have to deal with too much crossover from that perspective. I think I'm in pretty good shape here, honestly. I may have a couple of odd things where I have to flip things around or pay really close attention to traces, but I'm pretty happy with this overall. I think I can route it without too much difficulty. The size of this is 43.18 millimeters wide and 40.6 tall. So it certainly fits within the small footprint that gives me the discount that I'm looking for. So I am pleased with that as well. Can I make it any smaller? I probably could if I wanted to get really picky about it, but I am happy with where this has ended up, and I really do believe I'm going to be able to route this pretty easily.
Well, I am so pleased to get here. I am finally to the point where I am creating PCB designs and preparing to place an order. I've got a little bit more left to do. I've got to route the control ROM module, and I figured it would make this video just a little bit too long, and so I'm going to boot that into the next video. I also need to clean up the control ROM control module. That's got a little bit of work to do, but I should be able to get that done relatively quickly to the point where I can actually get into the control ROM control PCB design as well. Coming up here shortly, I'll be placing a PCB order, and I've got some supplies to order so that I can start soldering those up. But in the meantime, in the upper right hand corner up here, I have a playlist that is specific to this journey with the EEPROM replacement and how we got to this point, if you're interested in binging that. We'll see you soon.